Good afternoon, everyone, and welcome to session number 2 of day 1 here at ETE 2021. I'm Matt Swartley with Chariot Solutions, and I'm here to introduce you to Ricardo Gerardi, who is a senior consultant at Red Hat Canada and the author of the book Powerful Command Line Applications in Go. Ricardo is going to speak with us today about the power of Go interfaces, and this talk is particularly interesting to me because I recently started on a project where we're using Go after many years of working primarily in Java. And so I'm personally am looking forward to Ricardo's insights on how to use interfaces to make my Go code better. So please welcome Ricardo Gerardi.
Thank you. Thank you for the introduction, and thanks everybody for attending this talk. I'm really excited to be here and share the stage with such big names in this industry. And obviously, it's May the 4th, right? So for all of the Star Wars fans out there, May the 4th be with you. I am myself a Star Wars fan, so you're going to see a few Star Wars references sprinkled throughout the presentation here, some of the examples. As a little bit of a background, I'm not a I'm not a professional software developer, right? So I've been working in this industry for many years, but mostly as a consultant, and I've also worked as positions that would be more related to sysadmin or DevOps nowadays. So my experience with Go, it's really related to writing command line applications, because that's what I've been doing throughout the years with other languages before, and now mainly with Go. So I'll try to bring some of that experience here and inject some of what I've been doing with the language and how we can use it for that end as well. Related to that, I am the author of the book, Powerful Command Line Applications in Go. And this book is in the final stages of review now, so it should be, the final version should be out really soon. And the book came from when I started working with Go to write command lines. As I mentioned, I've been working as a sysadmin, as a consultant for many years, and writing command line tools was always part of my job. I had to write command line tools to do data analysis, to process logs, and to help monitor networks and systems. And about 3 or 4 years ago, I got in touch with Go. And one of the reasons was because I was also starting with containers, and some of the container tools out there were developed with Go, like Docker and Kubernetes, and now also OpenShift and some others, right? And I wanted to make some contributions to those projects, so I started getting in touch with the language. But then I started also using it to run my projects and the command lines that I was using for work. And there were a few reasons why I particularly liked Go for that. Go is a simple language, so it was easy to pick up and become productive with it quickly. I'll cover a little bit more of the simplicity in just a few minutes. Another thing that I like about Go is that Go combines the reliability of statically typed languages with the flexibility of dynamic languages. So you have the compiler and you have the protection, that it brings you, but at the same time, it feels like you are programming in Python. It feels like you don't have to. You don't need to create too many abstractions to get started. You can go straight to the point and then become productive really soon. Also related to command line applications, Go doesn't have runtime dependency. So Go compiles into a single binary. And that was great for when you need to distribute that application to many different types of servers. When you're running with, especially with dynamic language like Python, just as an example, you sometimes develop your applications in your laptop, for example, but when you try to run in a different system, then you have a problem, because sometimes you don't have the right version of Python, or you may not have some of the libraries that you require there, and you have no permissions to install those libraries with pip, for example. It sometimes makes it hard. And Go compiles into a single binary. You send that binary, you copy it to the machine, you run, and it tends to run, right? And associated with that, Go is multi-platform and is also cross-compile. So I can write a program for example, Windows on my Linux machine, and then just copy it to the Windows box, run it, and it runs. And obviously, some of the features that are Go is very famous for, like built-in concurrency, right? So it was also one of the ideas at the beginning. We were having some problems with performance in some of the block processing applications that we're developing, and then the concurrency features really came in handy. When we talk about the simplicity of the language, there's actually this phrase that's from Rob Pike, who is one of the creators of Go: less is exponentially more. And the idea there is that Go is simple. Go has a reduced set of features, especially if you compare to more traditional object-oriented languages. But those features are very expressive. Go is a very readable language, and is also very opinionated. And I know that this is sometimes a point of divergence in the community, right? But Go is very opinionated. There is usually one way to do things, or at least one recommended way to do things. But it makes it easy to use. For example, Go is object-oriented. You can do object-oriented programming in Go. However, Go has no classes. For example, Go has no constructors. It has no inheritance. Therefore, it has no type hierarchies, and it doesn't support method overloading. And it also doesn't support generics, at least not right now. There is a proposal for introducing generics into the language that was accepted recently, and they're aiming to get that by the end of the year, at least in a beta version. But so Go doesn't have some of the features that are very common in the most popular object-oriented languages out there, right? But if you don't have those features, how do you create code that is reusable? How do you create code that is extensible? And that's when we get to the point of our talk here. You use interfaces. Interfaces is my favorite part of the language. So I came to Go for those reasons that I described, and like the concurrency being a big one. But when I started using the language on a daily basis, I actually found that interfaces was really the appealing feature of the language. I sometimes can write programs in Go that don't use concurrency at all, but it's almost impossible to write a program in Go that doesn't really use interfaces. And interfaces are very powerful, and that's what we're going to be talking about today. Just a brief there in terms of interface. I know that for some of you, if you came from a language like Java, for example, or C#, very traditional object-oriented languages, interfaces is a concept that is common to you. For people that sometimes came from other languages that are dynamic in nature, they may not be as familiar, right? The idea with the interface is, it's at least in the object-oriented world, right? Because interfaces is a little bit of an overloaded term, right? The idea is that it's a way for you to make two entities that seem to be incompatible to interact with each other. And the example, or the analogy that I have here is of the power outlet. So imagine that you have the power outlet, right? And you are trying to plug in your device to turn it on. You really don't care about what is on the other side, right? Where the power is coming from. That's hidden from you. It could be coming from the power grid, maybe coming from solar panels or a generator. It doesn't matter. As long as your device knows how to connect to that and extract what it needs, that's all needs to work. And at the same time, the power grid, let's say, doesn't care about which device you're plugging in. As long as the device knows how to interact, they can connect and they can work together. And that's the same idea with interfaces in programming languages, right? It specifies a set of methods that an object has to have to be able to interact with other objects, right? It defines a contract. So if this type of this object knows how to do this, then we can use that type or that object in a specific situation. And it's usually, it hides the implementation. It's just the definition that matters, right? So you don't need to know how the methods are actually implemented for them to work. Interfaces in Go are basically the same thing, right? They define the behavior of your types. But there are some features of interfaces in Go that make them interesting. One of them is that it's the only way for you to do abstraction in Go. So you have concrete types and you have the abstract types, and interfaces is the abstract type in Go. So pretty much all of the abstraction that you're going to do, you're going to be using interfaces for. They define the behavior only, and then there's two items here that make them perhaps different from other languages and interesting at the same time on how we use them in Go. One is a characteristic, so they are implicitly satisfied. You don't need to declare that an interface or that a type implements a given interface. Just the fact that that type has the methods of the interface means that that type implements the interface. It's implicitly. And interfaces in Go, they tend to be small. It's very common in Go for you to have an interface with just a single method or two methods. And because they're small, they create powerful abstractions. So we'll take a look at that. Just in terms of general ideas here, not sure how much familiar I know all of you are with Go. And this will make easier to understand some of the examples, right? So we have the concrete types in Go. So concrete types, types that define usually data, right? The layout of data in memory. And you can have a few ways on, for example, how you can define types. So you can declare variables of a specific type, like var power of type int. So that variable is of an integer type. You can define complex types, like user-defined types, like in this case, the Jedi type, which is a struct that has all of those fields. And you can also define variables within functions. You can define variables using these the column equals operator, which initializes the variable, defines and initializes the variable. In this case, the compiler infers the type of the variable. In this case, for example, name will be of a string type. And it, as I mentioned, this feels like programming in Python. You don't need to define everything. The compiler will infer it to you, but then it's a statically type. After you define this variable as string, it will always be a string. So if concrete types define the data, how do we define the behaviors in Go? We define behaviors through methods. And methods in Go are just like any other functions, which again, it's expressive, right? So you can attach methods to types by providing one additional parameter to your function definition, which is here, in this case, J for Jedi, for example, and that parameter is called the receiver. That's the receiver is a parameter where the method applies to, right? So in this case, I can use J inside this method to reference the original type that I'm working on. That will be similar to this in some other languages, right? But the other interesting thing about Go is you don't have to define you don't have to define methods only on complex types like structs. You can define methods on any data representation. So you can do something like this. You can define a new type, in this case power, that will have an underlying type of integer, and then because I'm defining this type now myself, I can attach a method to that type. So in this case, the method unleash will apply to the type power. And to define an interface in Go, it's similar to defining a user type. You use the type keyword, the name of your interface, and then followed by the interface keyword and the set of methods that you want to implement. Okay, so let's start dealing with some examples on how we use interfaces in Go. As I mentioned, interfaces are implicitly satisfied in Go, and that brings some interesting concepts on how we use them. This is an example of using interfaces, and then a little bit later we'll talk about defining and interfaces and modeling some objects. But imagine that we have this program here where we defined in the package main. So that's how usually a Go program starts, right? It starts an executable. It starts in the main package with a main function. So this is an executable program. In this case, I'm importing a standard library package called FMT, which is usually common. People call it font or format. And then I define that same type that I defined before, Jedi, and then I instantiate that type into a variable loop that will be of type Jedi with some properties here, and then I print that variable out. By the way, just as a fun fact there, I didn't really know what was Luke's age, and I did some research. So he was 22 at the time of Empire Strikes Back, which is my favorite film on the franchise still. But if we print this variable now, what Go will do here is it will just print a representation of that variable. We didn't specify anything. Go is just printing. It uses reflection in the background to understand what the type of variable is, and then it prints what it thinks is the good representation of that variable, which is curly braces and all of the values. But what if we want to define our own representation of that type? We can use this method here. So the method string that takes no arguments and returns a string. I define that method on the Jedi, and I just say, okay, if this method gets executed, returns the first name, last name, first space and last name. Right? And the simple fact that I define this method in this type changes the behavior of the language, because there is an interface that the font package defines, which is called the stringer interface. And that interface, when we define this method, it will be implicitly satisfied, which means that when we run this program now, we just get what we want. But notice that I didn't have to define that this type implements any interfaces, right? It's just the fact that I defined a method that has the correct signature here. And when I was printing, the print function knows that if that type has that method defined due to the interface, it should use that method instead of doing anything else. And it works because of that. Again, there's no magic there, right? So that's the definition of the interface that we're using here, right? It's called the stringer interface. And this is not a built-in in the language. This is part of the standard library, but this is not built in the language. It's not like we're inheriting a method or overloading it, or we're not. We don't have something like a toString that we have, for example, in Java. It's not like that. It's just the fact that I defined a method named string with the correct signature, and Go was able to use it automatically or dynamically. And defining interfaces in Go like this is a very common pattern. So you have interfaces with, for example, single method like string, and then the name of the interface becomes the method plus ER, like stringer in this case. And we're going to have other interfaces that we're going to use that are similar to this. One thing to notice here is that by having implicitly satisfied interfaces means that we don't have unnecessary dependencies between packages. In fact, the Jedi type may not be aware that this interface exists. I could, for example, rewrite this with a Jedi type in its own package. So I'm creating, let's say, a library here, right? The package name is force. I define the type Jedi again, and I define the same method. And again, I'm not importing the font package. I'm not importing the interface. I'm not. There's no implements keyword here. I'm not saying anywhere that I'm implementing the interface. But if I go now to another program and I import the package that I just created, the force package, and then I import also the font package because I want to print that value, and I run the same code again, it will do the same thing. And I didn't have to define any kind of implementation explicitly. And that's a very interesting concept, because we're going to see a little bit later how you can use those to define interfaces more at the edge. Instead of defining interface where you define the packages, you define the interface at the point of use, and that has some interesting consequences. We'll get there in just a few minutes. And another characteristic that we mentioned about Go is that Go has small interfaces, like the string interface, right? There are many others in the standard library, and it's a common practice, even when you're creating your own interface, to define small interfaces, right? The fact that you define small interfaces create really powerful abstractions. So in this case, for example, don't need to learn or to know everything here, but the idea here is that we have the main function again, where we create a file, and then we have a function here at the bottom called named save, that takes, let's say, a pointer to a file as an input and some data stream to write, and then it writes the data from the data slice to the file here. We can execute this program, and it's going to write the data. It's writing the data on a file on the background, right? That's not really important at this point, but we're writing the data to the file. There is really nothing wrong with this program. If you really, what you want to do, the only thing you want to do is write into file, this program works. But the fact that you are requiring a pointer to a file really restricts your function. It can only be used with a pointer to a file. So you need to create a file, you need to have a file open, and then you need to pass that file to the save function. So that makes it harder to reuse this function or even to test that function. So how can we make this, or how can we improve this a little bit more using interfaces? We can use another interface from a standard library called the IOWriter interface that has only one method. It's the method write, and it takes a slice of bytes, just like a variable size array of bytes, writes it to whatever it needs to write that, right, and returns the number of bytes that were written, or an error in case it could not write that amount of bytes to the destination. By using this interface, we can rewrite our program now. You see that we can rewrite the function save to take now an IOWriter interface. And we don't have to change anything else, because the pointer to file here, in this case, the file type, it has the method write that follows the same signature as defined in the writer interface. And because it's implicitly satisfied, which means that we can now use the same code, we can use the same file, but now we're taking an IOWriter as input instead of the file descriptor or the file pointer directly. And if you run this program, it's the same result. It writes the data to the file, but now our function is getting more flexible, because now we can accept other things. So for example, we could expand this program. Now imagine that now I'm creating, this is a separate program, just to show the idea here. In this program, I'm creating a TCP listener. And this TCP listener is listening on port 3000 on my local machine. And whenever a connection is made, I handle that connection by reading all of the data coming from the stream and just printing it out. So not very fancy, but the idea is that we're getting that data from a network connection. Right? So I will run this program, and it's listening now on port 3000. I'll leave this program on the background, and I'll go back to our first implementation of a program. It is the same function that we had before, the function save, but at this time, instead of passing a file, I'm defining a client here using the net.dial function, which creates a net connection, a network connection. And this network connection also has the write method, similar to the file, which also satisfies the writer interface implicitly, which means that if I pass this client now to that function, I try to save, what I see is the same result here. The data was written. But if I go back to the TCP listener, I can see that the data, some data to write, was written to the TCP connection and was displayed there, because that's how we're handling it. So again, the flexibility increased, right? And because these interfaces are small, we can extend their usages, right? We can do something like this, for example. We can rewrite, or we can write a wrapper, for example, what's called Logwriter, where I take a writer interface, an instance of a writer interface as input, and I return a writer interface as output. In this function, I just return a new type that I created called Logwriter, and that defined with the original writer as its only property here. And that type defines its own write method. Similar situation, because I don't have to declare anything. I can just define this method here with the same signature. And now I can print. It's like a log printer, right? So I can print the content to screen, for example, and at the same time write it to the final destination. Similar to a decorator in other languages, but it's a very common pattern, right? So if I run this, I can see that the data was written here. And if I go back to the TCP socket, I can see that the data was also written to the TCP socket. So the fact that we can define a small interface and they're implicitly satisfied, gives us lots of possibilities on how to use. And this is, as I mentioned, it's a very common pattern, for example, to create middlewares when you're talking about web applications, or intercept data for APIs, for example, in injecting other properties in the data, for example. That's a very common approach. Interfaces also help you a lot with testing. So that was a particularly interesting problem for me when I started working with Go. One of the things that we wanted to do is, because these tools were becoming more and more important in our environment, we wanted to make sure that the tools were not just there, that we were really testing them. They were becoming critical to the infrastructure, even though sometimes they were a small command line application. They were really becoming critical to make sure that all of the IT infrastructure was working. So we wanted to test, right? Testing command line applications sometimes may be hard because you have some restrictions. Sometimes, for example, you need to test the output that goes on screen or on the error stream. So how do you intercept those things? And again, interfaces makes it a little bit easier to do those tests. So going back to our save function here, right? We go back to the first implementation where we're taking a file. And because we're taking a file, when we write a test save to do unit tests on this function, we have to add a lot of boilerplate code here to create a file, to pass that file to the function. It's because the function requires a file, that there's no other way, right? We have to create a file here. We have to create a type, a value of type pointer to a file, pass it, and then we have to read the data from the file and then decide, do the testing and then decide if the test pass or fail. And notice that the two highlighted lines here are the only lines that are really testing the actual business logic. Those are the only lines that are relevant for us as a business logic for testing. All of the other lines are just dealing with file, creating file, reading to the file, and making sure that the file is cleaned up after, right? Because you have to deal with all of those things. But if instead we have the other version of our save function that takes an IOWriter as an input, then we can replace the implementation during the tests, and we can use other types that also have that same method defined. So for example, in this case, I don't even have to define like a mock type specifically for myself. I can use from the standard library a buffer. So this is comes from the bytes package. This just defines a buffer of bytes in memory that has the right method. So I can write to that buffer, and then I can read from it later and compare if the data that was written matches, and then pass or fail the test accordingly. So this function is linear. It's clearly it's easier to understand, right? And it allows you to do many options of testing without having to implement methods that may be unnecessary for your testing. Duck typing. So that's another concept that is very common in dynamic type languages or dynamic language like Python, for example, right? The idea there is if he walks like a duck and he quacks like a duck, then he must be a duck, right? So the idea is that if you have an object that has some characteristics, you can use it in different places, right? Go can do something very similar, but in Go, I would say that I would redefine this sentence in if it walks like a duck and it quacks like a duck, then it behaves like a duck. And there's an important distinction here that we're going to get down when we're seeing some of the examples, right? The idea is that by using interfaces, you can do something similar to duck typing that you have in Python, for example, but that's guaranteed by the compiler, that you're not going to have some obvious mistakes like providing the incorrect type and then having a runtime failure, right? So if you do that, it's going to be a compile time error, and that's much better than having your application fail in the middle of the execution, right? Let's take a look at an example, right? I think there's a joke for Go, right? That's usually when we're talking about interfaces in Go, there's two classes of examples, right? The ones based on shapes and the ones based on animals. I decided to go with the shapes one, right? It's a little bit contrived, but it illustrates well the point. So we're defining a package here, so a library that we call shape. And in this package, we define two new types, a circle type and a rectangle type with their respective fields. And then we define the method perimeter that takes no arguments and return a floating point number. And the same thing for the rectangle, we define a method perimeter that returns a floating point number, and that calculates the perimeter of that shape. Notice that we're not defining any interfaces at this point here, right? Well, how do we use these objects? If you want to use these objects in a function, in a common function, something that is flexible, we cannot use them directly because they are not the same type. But we can use the behavior to make them compatible. What we do in this case is at the point of use, and see, not at where we define the shapes. At the point of use, we're defining a interface that we call border that specifies only one method, perimeter, that takes no arguments, returns a floating point number, and then any objects or any types that have that method will implicitly satisfy this interface. And any types that can satisfy this interface can be assigned to a value of this type. So we can use different types as a type border. And that's what we do here, right? So we, for example, we create a function that we call print border that takes a border as input, like a value of a type border here, interface border. And then we can create two objects. We can instantiate a circle, a rectangle, and then we can use the print border on those on both of those objects. And the function works because both of those objects implement that interface, and therefore they can be used as that type in this case. And it goes beyond, right? We can do more things with this. So we can extend, again, because the interfaces, and I'll keep going back to that point, right? Because the interfaces are implicitly satisfied. We don't need to declare them. We can do things like this. We can define a new type right here. I'm not defining the square type back in the shapes library. I'm defining the square type locally here, and I can embed the rectangle type from the shapes package, from the shape package into the square. By embedding a type in Go, you are creating a new object that extends, may not be the proper word, but it has the same fields and the same methods of the original type, but it's a new type. And Go has something called inner type promotion, which means that the square type, because we're embedding the rectangle, the square type has direct access to those fields and to the methods from that embedding type. And because of that, they will implicitly satisfy the same interfaces. Just to make sure that we're creating a square, right, with the same side length and width here, we're creating a function here to create a new square. That's kind of a constructor, but Go really doesn't support constructors, not in the same sense as other more traditional languages, right? But you can create some functions to return the object and do some initialization when needed. In this case, we create this function, and you see that it's the same code as before. We define the circle, the rectangle, but we also define a square now, and we can use the print border function to print the border of the square, and that's because the square is implicitly satisfying that interface just because we embedded the rectangle type into the square type. But what is interesting here is that you have to remember that composition is not inheritance. Go doesn't support inheritance. There's no type hierarchies, right? So a square is a completely separate type. It has the access to the methods and the fields from rectangle, but it's not a rectangle. If you try to use that, if you create, for example, in this case, we're creating a slice, which again is like a variable size array of rectangles, and then we assign a rectangle to it, and then we try to assign a square to it. This is a compile time error because Go knows that a square is not a rectangle, and you cannot use that. You cannot use the type square where you're going to use a rectangle. So how do we group things in Go? We use interfaces. We group them through their behaviors. So what we can do in this case is this very similar code, but instead of creating a slice of rectangles, we're creating a slice of borders, right, of interface of type border. And now, because all those three objects or three types that we defined before, they match the signature and they satisfy this border interface, we can use them as part of that collection as a border. And we can do a for loop here, for example, and then we can print the values for all three objects. So all three objects now are part of the same array, the same grouping. However, there's one situation, right? So imagine now that we want to augment that first shape package. We are adding more methods to our types there. So we're adding an area method and for the circle and the rectangle, right? So now, if we try to use that method that we added now directly from a value of type border, this will fail. And it fails because the type border only defines the perimeter method. It doesn't define the area method. Even though the underlying concrete type has the method area, because we're using the interface to represent these objects in this loop here, it has no access to those additional methods or even properties, right? So how can we expand this concept now, right? A very typical approach in Go is not to change the original interface. So we're not going to change the border interface. We could, but that could bring other issues. Like now we have to make sure that everybody who is using that interface is updated, and right, have to make sure that it's not going to break anything else. So a typical approach is to compose interface. So we can create another one method interface. In this case, we're calling the interface named surface that defines the area method. And now all objects or all types, right, that have the area method will satisfy this interface. At the same time, we create another interface that we call surface border, and we embed those two original, the original interface border and the new interface surface. Now we have another interface that is a combination of both the border and the surface interface, but we also have the surface interface as a separate entity. And we can use them in different cases. So for example, we can create a function now, print area, that takes only a surface interface as input, because the only thing that we require here is to use the area method. But at the same time, we can define our slice now with the type surface border interface, because we want to group those objects, and we want to have access to both the area and the perimeter in the main function, right? And it's the same thing now. If we run this example now, we can print both the border and we can print the area, right? The perimeter and the area of all of those types. And that's one very interesting point about Go is because these interfaces are implicitly satisfied, these types, they can at the same time, they can satisfy multiple interfaces, even if they're unaware that they're doing that, right? It's just the fact that they define those methods will cause the interfaces to be satisfied. Now into just a few more examples. So we're talking about how to use the behavior to get access to additional methods on the types, right? So, and I tend to use that approach a lot every time that I can. That's it's more extensible approach. It's easier to test. It has some of the benefits that we already mentioned, right? But in some cases, you may need access to the concrete type underlying, right? So let's talk a little bit about some of the additional features here. If you need access to the concrete type that is underlying the interface, what you can do is you can use type assertions. So a type assertion is this construct here where I take the interface value, which is S, and I try to assert that value as a shape.circle. So I'm saying this has to be a shape.circle. If I just do this without an if condition or anything, and the type that I'm asserting is not a circle, that's a panic. So we want to avoid that. So what we do is we use this syntax here, which is very common in Go. It's called the comma OK syntax. So this call here will return two values. So one is the type converted to the asserted type. So if this assertion works, C will have is a new type that has a circle as a type now. It's a new variable that has a type circle. And it will also return OK. OK is a Boolean saying that whether or not the assertion failed or succeeded. If it succeeded, then we can access the parameter radius right from the circle. And if it's going to fail, for example, for the square or the rectangle, we don't go there because both those types, they don't define the radius, right? So we can run this now, and you can see that for everything, it prints, again, the border in the area. But for a circle, it also prints the radius because it asserted that for that iteration of the loop, it was a circle, and it could safely print the radius. And there's another construct that is called type switch. So a type switch is similar to what we're doing, but instead of going in an if condition one per case, we can define a switch statement that tries to assign or tries to assign a type to the new variable that we're calling C here. It's using assertion again, but now each case statement becomes one specific type. So in this case, we were trying to assert in the first case that if it's a shape.circle, then print the radius. If it's a rectangle, then print the length. And if it's neither a circle or a rectangle, just print not one of those, right? And if we run again this program, we print the length for the rectangle, the radius for the circle, and in the case of the square, we just say it's not a rectangle or a circle. So that's some of the ways that you can use Go to dynamically understand what is behind the interface and then access it and use. As I mentioned, I try not to use that as much. I prefer the approach of sticking with the interfaces, but in some cases it's unavoidable, right? And finally, we're not going to go too deep into that, but at least to mention, there's something else in Go called the empty interface, which is defined by interface, open and close curly braces, right? The idea there is, again, the empty interface is not like any kind of a magic, right? Because interfaces in Go are implicitly satisfied, when you create an interface that has no methods, you are basically saying any type that implements no methods satisfy this interface, which means that any type can satisfy this interface, because any type implement at least 0 methods, right? So the idea here is you have a very generic type in Go that you can use to hold values of any other kind of type. But I would say that I avoid using the empty interface. There are some programs that require it, and the standard library in Go uses it, especially in conjunction with reflection, to infer some of the types and do things there. But using the empty interface removes some of the guarantees of the compiler, right? So there's another phrase from Rob Pike who says that the empty interface says nothing. So now you're using a compile language with a type safety, but you're using an object or a type that describes nothing, and you suddenly lost all of that protection from the compiler, because you're going to have to do those checks at runtime, because only at runtime you're defining what is in interface. So they're often misunderstood, and I usually try to avoid using them, but obviously in some cases it's required. Okay, so where can you learn a little bit more? So these are some of the links that are really useful for learning more about interfaces. The first one is the Golang tour, where you can run some examples there, right? And then some great blog posts about the very deep inner works of interfaces that I recommend. And by the way, I will make these slides available at GitHub, and then you're going to have access to those links. As a summary, interfaces are one of the most powerful concepts in Go. They really improve your programs, they improve the readability, the reusability, and testing of your Go programs. They are implicitly satisfied, which means that you can use them in many different ways. And they allow you modeling complex behavior using simple types through behavior. For those who are interested in the book, I'm leaving a link also here at the end. And then the first link is the link for the book page itself. The second link is a link to a coupon where you can get the book with the discount. And I will open up for questions now, and also after the talk, I will be available on the conference Slack, but I'm also available usually on Twitter. This is my Twitter handle. So if you want to continue this conversation, please contact me on Slack or Twitter. Thank you.
All right. Thank you very much, Ricardo. Appreciate you coming here and sharing all that knowledge with us.
Thank you.
We've got a few minutes left, so if there's any questions that anyone is interested in having answered while the session is still going, we can entertain those either from the Zoom chat or from the Slack room C. And then I would also encourage you that just because the session has ended, don't let that stop you from asking questions. Let's try to keep the conversation going on the various conference Slack channels. All right, so there's some kudos coming in for the Slack channels for sure.
Thank you.
How long have you been working with Go, Ricardo?
I've been working with Go for 4 years, about 4 years now. Yeah.
And it was something that was kind of not forced upon you, or did you take it upon yourself that you found an interest in the language before you were using it day to day?
Yeah, so it was really not forced. It was a choice, and I was one of the ones that brought that to my previous company, and we started doing things in Go. And as I mentioned, it's because it was really suitable for the specific case that we're using, like writing command line tools, processing logs. I remember one case where I was doing something with, I used to use Perl a lot before, and we're processing, I don't know, millions of lines of logs, and it was taking a while, right? And then we brought Go, and it would process the same file in a matter of minutes, right? So the performance was something that at the beginning was really interesting, but as I started programming more and more with Go, I started seeing some of the other features like testing, like interfaces, and yeah, and they're really easy to use and they're really cool.
Definitely, thanks. Yes, I think there's a comment here in the chat saying that probably most of the questions that people wanted answered were you addressed already in the talk. So, okay, well, it doesn't seem like there's too many questions, so I guess we'll sign off from here. Sorry, there's one here just before we go. The question is, what feature did you mention in the beginning that will be added to Go?
It's generics. So generics closer to what generics are in other languages like Java, for example. So a proposal has been accepted for that, and it's in the works right now.
Okay, and here's another quick question. Do you think that the way Go handles object-oriented principles using interfaces is preferable or better than the more traditional ways, such as inheritance, method overloading, etc.? That's from John Wills.
Yeah, perfect. Yeah, that's an excellent question, right? I wouldn't even say that they're better or worse. It's definitely different, right? And it took me a while to get used to doing those things. One thing that I like about that approach, when I compare, for example, with more traditional language like Java, is in Go, you can get started quicker. So you don't need to define too many abstractions at the beginning before you can start, coding. So we used to say that in Go, you start on the concrete, and then you start discovering some of those interfaces and abstractions as you move along, and that's a very interesting concept. It's definitely different, and I think it stays a little bit, let's say, in between more traditional object-oriented like Java and dynamic languages like JavaScript, for example, that don't use this concept at all. So it's a kind of an in between, and I like it because of the productivity that I have with it.
Okay, great. Thanks very much. All right. Well, to all the attendees, thank you for stopping by. We've got a little bit of break for before the final session of the day. So, and thank you again, Ricardo, and we'll see you all in the Slack chat. Thanks very much.
Yeah, thanks, everybody. I'll be there in Slack.